In this video, I'm going to demonstrate how to get factor scores from SPSS that correspond to a particular factor solution. And in this example, I'm talking about intelligence, and this carries forward in the textbook where I estimated factor scores across 3 different methods, and I'll show you how to estimate it across all 3 methods. I'm only going to do it for one, regression / Thurstone, but I'll show you what button you need to click in order to get the different types of factor score estimation methods that I describe in a fair amount of detail in the textbook. So in order to get the factor scores, you have to conduct the factor analysis and specify everything that you want, estimation and rotation, and then you got to click on an extra button. So let's go back, analyze dimension reduction factor, and these are the variables that I want to include in the factor analysis, all 9 of them. And I put that like that into the variables box, and then I click on extraction. I want to make sure that I'm using, I think it's maximum likelihood I used in a textbook. I want to extract 3 factors. I know that based on the parallel analysis I did. I'm going to rotate. In this case here, I'm going to use Promax because I think that's what I used in the textbook, and click continue. And then scores is what you're going to need, although technically I like to sort the factor loadings by size. It has no consequence on the actual results you get whether you sort the factor loadings or not. So to get the factor scores, click on scores, and then you want to save them as variables. And what's going to happen is that SPSS is going to create, in this case, 3 different variables that correspond to the 3 factors that we know reside in the data. And here are the methods of estimation for the factor scores: regression, which is also known as Thurstone, and then Bartlett and Anderson-Rubin. And Anderson-Rubin gives you uncorrelated factor scores as I describe in the textbook. And then there's some differences between regression and Bartlett that I talk about in a fair amount of detail. Overall, I actually prefer regression-based factor scores because they're the most correlated with the factors of interest. I would rather deal with the correlations between the factor scores in other analyses like multiple regression rather than trying to deal with it in the factor score estimation approach. But that's your choice. There are pros and cons across all 3, and you can choose which one you want. You click continue, and then you click OK, and SPSS will generate the factor solution. The entire factor analysis is conducted, and that is similar to what we got for maximum likelihood factor analysis with direct Obermann, but a little bit different because it's Promax rotation in this case. The important thing is that now I have these 3 new variables in SPSS, and they don't have terribly illuminating names. So you get FAC 1_1 and then 1, 2, 3. Very non-descriptive, and then even the label is not descriptive. So SPSS is not smart enough in order to label your factor scores consistent with the actual nature of the factors. But we do know by looking at the pattern matrix that the first factor scores represent memory span. So I might call this GSM. This is from intelligence research that we refer to the memory span factor as GSM in short form. And then the second factor looks like fluid intelligence, or GV. I'm just going to go with GF, even though I think it's somewhere between. So fluid intelligence is the name of that factor, and those factor scores. And then the last one is processing speed, coding symbol search cancellation. So I'm going to call that GS. And you can add labels here like fluid intelligence. Whoops. I can't type at the moment. Fluid intelligence factor scores, if you wanted to. Write it like that. Whoops, actually it was memory span. Factor scores, fluid intelligence factor scores, and processing speed factor scores. And from there, I've now got my factor scores. We can look at them and see if they correlate with each other. They will. So let's actually look at the correlation. Let's just put this window in such a way that you can see it. And then I click on OK. And we can see that there are some really big correlations between these factors because these dimensions of intelligence are known to correlate in nature. They're not exactly the same correlations between the factors estimated in this methodology because it actually is slightly different estimation methods, but you'll get similar types of correlations across the factor correlation matrix and the correlations between the factors. Now, once you actually have your factors, or I should say your factor scores, and you've named them, and notice that there's a mixture of positive and negative values, and that's because factor scores are standardized scores. So they're not anything other than scores that would expect to have a mean of 0 and a standard deviation of about 1, but they won't have that exactly. You'd actually have to standardize them yourself. Let's just actually check that. Let's see the means and standard deviations just for fun. Yep, mean standard deviation, and let's see what we get. A mean, oh, you know what, we actually almost get exactly 1.0 as standard deviations, but not quite. So they're not exactly perfectly z-scores, but they're close, with a mean of 0 and a standard deviation of 0.92 to 0.93. I then talk about using factor scores. I mean, the reason why we get factor scores from a factor analysis is because now we want to use these scores to predict things, either a correlation, but they can also be used in a t-test or an ANOVA as a dependent variable. The options are pretty much limitless in terms of how you can use factor scores. In the textbook, I talk about using the scores to predict video game playing ability, and that is the dependent variable in this case, and I would put the video games variable there, and then I would put my factor scores as independent variables. And if you have looked at my chapter on multiple regression, I like looking at partial or semi-partial correlations in the context of regression, and I'm going to do that here, and I click on OK, and now I've got a solution for multiple regression whereby only one of the dimensions of intelligence was found to be a unique predictor of video game playing ability, and it's the processing speed factor scores with a standardized beta weight of 0.35, significant p less than 0.001, and the semi-partial correlation is 0.266. The zero-order correlation between processing speed and video game playing ability is 0.36 rounded, so it has decreased to 0.27 rounded. And that's because it's shared variance with the other dimensions, which is part of the reason why we do multiple regression, is because we want to uncover unique effects. In this case here, memory span had a standardized beta weight of 0.04, so almost 0, and the p-value is 0.678, not significant, and fluid intelligence negative 0.04 in round terms, and also not statistically significant, and the semi-partial correlations are also pretty much close to 0. So in this case, we can say that processing speed is the only unique predictor of video game playing ability, and we uncovered this by obtaining factor scores that best represent the dimension of interest, in this case processing speed, and the same is said of the other two dimensions, which were not found to be unique predictors. So this is a good example, I think, of using factor scores in order to enhance a research study that wants to predict a particular criterion with dimensions that reflect constructs or factors, if you will.